record. All right, concept of Fourier series. Yeah. 28th, 2 weeks. Yeah. All right. All right, so Fourier series, we're going to talk about what a Fourier series is. Some of you guys probably already know. You may have seen that in math, but I'm going to talk about it a little bit more from an engineering perspective, what it's about. So if you look in the book, it's chapter 9. All right, section 9.1 is really kind of the main section, which talks about the 3 different forms of the Fourier series. What I don't like about the book on this is there's a lot of equations, and you can easily get lost of them. All right, so I'm going to try to simplify those equations because, to be honest with you, they don't need to be so many. There can be fewer, and I'll kind of simplify those here. And then section 9.2, which deals with common signals. We started talking about common signals, things like steps and impulses and stuff like that. There's certain common waveforms that we come across all the time, and nobody wants to derive all the Fourier series stuff for common waveforms. So there's some information about some sort of common signals there. All right, but I want to talk about why we care about this from an engineering perspective first. So we talked about 2112, and really all engineering problems really deal with what we call dynamic systems. All right, what did I say was the meaning of a dynamic system? What's the difference between dynamic and static?
Dynamic changes over time.
Dynamic has some change over time, right? If I had a network with 2 resistors like this, it would be a voltage divider. I'd put a DC voltage in, and all of a sudden the currents would be the same everywhere throughout the circuit. In a dynamic system, there's change over time. So if I have an RC circuit, there's going to be change. And what that means, and we've talked about this a lot, is the dynamic part gives rise to a transient response and a steady state response. The transient response basically, like I said, represents the memory of the system or its opposition to change. Like that capacitor, if you were a computer engineer, you look at hardware, right? If you look at a RAM chip, for instance, what's a RAM chip? Well, it's basically a bunch of capacitors, right? Capacitors are what stores voltage, and that basically, if it stores a high value, it stores a 1. If it stores nothing, then it stores a 0, right? So I think of a capacitor as basically being a memory element, and this transient response reflects that memory effect that it has. Okay, so in this case, I have a cosine going into this thing. So if I didn't care about the transient response, I just wanted to look at the steady state piece of this. The way I've shown this guy right here, this would be, I don't know, Vn of t equal to, I don't know, V cosine omega t, like that. What would V out look like? It would be a cosine with the same frequency. I don't know what its amplitude would be. I'd have to solve that, right? A cosine omega t. What else would I know about it? It has a phase angle. It's shifted and it's scaled from that input. And what's the way of figuring out this scaling? So I call this a scale. I call this a shift. Okay. What's the way of figuring out that scaling and shifting? If I don't feel like, one option is differential equations, right? So I can use differential equations to solve this. If I wanted to do it, it would be RC dV out dt plus V out equals V in, right? It would be this thing, right? And you could get that from KVL, right? No one likes that, right? I got to guess stuff. It's ugly. What's the other way that you've learned in 2112 and that we used in the project too?
Phasor analysis. Yeah,
phasor analysis, impedance analysis, right? So basically I can do impedance analysis with this, which basically lets me go back to just an algebraic manipulation. It becomes a much more straightforward thing to try to do. All right. So impedance analysis is nice because it says if I've got an input like this, all right, A cosine omega t plus phi, I thought of it as the real part of this thing, okay? And I said, I'm just going to take this thing we called the static, I called it the static phasor. In 2112, you called it the phasor, just the phasor, right? I take that thing, and I know that my output is going to have some amplitude and some phase, and I could use impedance analysis and phasors and do all of it, and basically got rid of T. Getting rid of T is what got the differential equations out of there, because it got the d by dt's out of there, All right, that's the thing that was really nice about it. Now, here's a question. What was the assumption for using impedance? What's the assumption? What has to be true about the inputs? Well, okay, you got it. Let me come back to that point. You're right. So, but what kind of signals in particular do I have to have? And you're kind of right by saying the frequencies have to be the same. But what kind of signal specifically do I have to have?
AC.
Not just AC. What does AC mean? AC means alternating. All right. They have to be sinusoidal. All right. They have to be sinusoidal. And AC and sinusoidal kind of means a little bit different thing. Right. And it has to be the case that there's only one frequency. So it has to be a sine wave with one frequency. And then in that case, I can solve for everything at that frequency. So what happens if I have this? This is what I would call an AC input as well. All right, this is a pretty common thing. Like I said, this is, if I look at what goes on in a memory chip, this is pretty similar to what it is. I have a VN, which is a square wave. All right, so this guy I'm going to call here a square wave, or, you know, this is really what I think of as a clock signal, right? So if I have that square wave going into this circuit, all right, this guy is periodic. He meets my definition of periodic. What was my definition of periodic? Back at the beginning of the semester, we made a definition of periodic. What was it? What do I say about x of t? What's it equal to? Yeah, x of t plus capital T. In other words, if I come back, if I look at the value of that waveform, one period away from now, it's the same. All right, that's my definition of periodic. This guy fits that definition, but he's not a sine wave, right? So the question is, can I use impedance analysis with this? Is there an opportunity to do that? No, there isn't. My basic assumption with impedance analysis was that Vn had to be a sine wave. That's not true here, right? In this particular case, it's a square wave. So what do I have to do? Well, I have to go back to differential equations. Well, that kind of sucks because we had this sort of beautiful thing that allowed us to get, it uses complex numbers, so it's weird, but you guys seem fairly comfortable with complex numbers, right? It lets me use complex numbers, but I can get away from using differential equations. And differential equations are awful, right, on a day-to-day basis, right? There's a lot of stuff going on there. So the question is there some alternative way of doing this? For those of you who know what Fourier series is, what is, I guess, the idea of a Fourier series, so if you know what it is, maybe before I throw that up there, what is a Fourier series, if you know what it is? Does anybody know? Okay, well, that's good. What it says basically is that this waveform right here, this sine wave, can be expressed as a linear combination of what I call periodic basis functions. All right, or in other words, this guy is a sum of cosine waves. Okay. There's a bunch of little cosines and sines that can add up to create this waveform. All right, now we're gonna look at this concept here in a little bit more detail here in the next couple of slides, but this is particularly useful. So what this says is if I can view this as a sum of sine waves, that means that if this was a voltage source, let's call this Vn of t. Okay, so if I put an oscilloscope right here and I called this Vn, I would see that. The fact that this Vn is equal to a summation means that I can draw another picture that looks like this. And I can say this is cosine omega t, and this is some other, let's say I'm going to call it cosine 2 omega t, cosine 3 omega t. Somehow I can take this thing and I can view it as a sum of other cosines. If I can do that, then what does this allow me to do? If I know how to do this, what does this allow me to do? instead of, so I liked the whole idea of having sine wave inputs because with sine wave inputs, I could use impedance. I said with a square wave, I have to use differential equations, but there's some way of making that square wave turn into a bunch of sine waves. If you had a circuit like this, where you had 3 different frequencies, right? So the one frequency is omega, one is 2 times omega, one is 3 times omega. If you had that problem, how could you solve that problem instead? You could use superposition, right? I know that's one of those things usually people are like, oh, I don't like that, right? Trust me, that's a lot better than differential equation. All right, and we'll talk about that. All right, we'll kind of see more about the meaning of that, but where would I use that kind of thing? Well, lots of places, right? So here's an example. What I have here is, I thought about, there's a couple of different ways I could try to express this. One would be, a lot of you guys have probably used an Arduino or something like that to drive a motor or a Raspberry Pi or something like that for robotic stuff. I think of that as kind of an embedded systems problem, right? Another embedded systems problem that I think about is something like this here, where what I have is what I call a PV inverter, all right? So a PV panel, a solar panel, outputs a DC voltage, okay? So if you looked at the output of a solar panel, you'd see a DC value, it'd be nice and flat. Now, it may not be all that flat because maybe as the sun goes behind the clouds, maybe it'll kind of go up and down a little bit, but it's flat. Over here, this is the grid, VG. So my goal was to take a PV panel, and typically it's not a panel, usually it's a bunch of panels, but I hook them up to the grid like this. What's the VG, V grid? What's V grid look like? If I looked at that on an oscilloscope, what would that look like? 60 hertz sine wave, hopefully. All right. Now, that's what it's supposed to look like. All right, it may not, but it's supposed to look like that. So VG would be something like this. It would be 60 hertz, which means it would be 2 pi times 60, 377 radians per second. And the peak to peak value here would be, if I was hooking this up to, let me ask this, if I was hooking this up to your house, what would be VG? What would be its peak to peak value? Any idea? So 120 is the RMS value. So maybe you started talking about that in 2112. That means it's 120 times the square root of 2 big. In your house, it would actually be 240. All right. We can talk about why that is. That's not all that important for right now. If you want to know, you can ask me later. But basically, this is a sine wave that I should get at the wall outlet. I think of this as an embedded systems problem, because what do I have? I got over here, if I had a single panel like this, and I shouldn't think of this, I don't know, I don't want to get too fancy. This guy's, let's say, maybe going to be 30 volts like that, okay, DC. And I want to get it over to the grid. So DC coming in, AC sine wave coming out, okay? What this is an embedded systems problem. This guy right here is what I call an inverter. All right, now I use the term inverter when you think of an inverter as what? When you've seen an inverter, you probably learned it in digital circuits. An inverter is a NOT gate, right? I put a 1 in, I get a 0 out, 0 in, I get a 1 out. This guy's pretty similar. What he does is he takes a DC value and turns it into an AC value. All right, it's a very simple circuit in theory. All it is some switches that are turning on and off. All right, the smarts of it are here in the microcontroller. All right, what comes out of this thing I call V sub I. So V sub I is this guy. All right, V sub I is a square wave that looks pretty weird, right? What is going on with that waveform? It's doing something that's represented by 3 letters. Some of you guys may have heard this. If you've done robotics, how do you drive the motors in a robot? PWM, what's that mean? Pulse width modulation. All right, what that is a pulse width modulated wave. All right, so I have a waveform that is, as it turns out, that waveform, this V sub I, is periodic. If it's periodic, that means it's represented by a sum of sine waves. One of the sine waves in there is this guy here, this sine wave, V sub, well, I'm not going to give it a name, but there's a sine wave that lies within that. that sine wave plus many other sine waves at different frequencies can be added up to equal that square wave pulsy thing, right, which we're going to talk about here in some more detail. But essentially, what I'm trying to say is this type of an approach, this is what comes out of this circuit, right? So V sub I looks like this ugly wave. What is the function of this Li, Lo, and C? It is to make it look like that sine wave. It's that same term I used before, a low pass filter. What it's doing is it's getting rid of all these high frequencies and turning this thing into this nice, pretty sine wave. All right. All right, who controls? So you're asking great questions. So so the frequency of V sub G is determined by the utility, right? They're just the generators in the world are making that happen. As the guy who hooks up on your rooftop or whatever, I have to measure that voltage, and there's some circuitry and some code that basically makes sure that this square wave here matches what's on the grid, right? So it's a control system problem to make that work. It's a classic embedded systems problem, right? To try to do this, I got to measure some stuff and then create an output based on those measurements. Okay. So Fourier series is a perfect tool for how I try to analyze and design this system, right? So figuring out how to choose these components right here require me to have some understanding of Fourier series and how I can take this ugly waveform and turn it into a sine wave. All right, there's a lot of places where we use that tool, right? A lot of places where we use that. Now, somebody said there that the wall voltage should be a 60 hertz sine wave, and it should be, right? This is actually what it looks like in the building here in Epic. All right. And it's scaled down so we could sort of safely measure it. It should be about 170 volts peak. But if I look at that, that kind of looks like a sine wave, but kind of not. If you look at it, it looks a little chopped off, a little flat at the top, and it's got those little shoulders or something that's developed there near the zero crossings. If I look at that, what I find is that this thing is periodic, so it's got a Fourier series. One of the things I didn't mention about these sine waves back here, which I'm going to talk about, is those sine waves are what I call harmonically related to each other. So anybody know what that means to say that they're harmonically related to each other?
Is it similar to music where it's like overtones?
Yeah, they're overtones, which means that they're multiples of each other. Okay. So in this case, this guy consists of waveforms at 60 hertz, 120 hertz, 180 hertz. What's next? 240 hertz, 360 hertz, so on and so, well, 300, I skipped one. So on and so forth, right? So basically, if I look at this, I give this a name right here. I call this my fundamental frequency. And everything else is a multiple of that. So my harmonics are n times what I call the fundamental. All right, so I'm basically getting integer multiples of each other. All right, so we're going to define those terms more, but basically I see it that I have something at whatever my fundamental is, and then a 2 times that, 3 times that, 4 times that, 5 times that, so on and so forth. And I can use a tool. We're going to learn how to compute the amplitudes of those sine waves. That's what Fourier series analysis is really all about. But I can have tools that basically look at a waveform and measure what's the amplitude at each of the frequencies. So in this case, what I've done is I've said, well, at the third harmonic, so 3 times the fundamental, I have this much amplitude. At 5 times the fundamental, I have this much. And then I can see it gets, at the 9th, so 9 times the fundamental, it's a little bit smaller. All right, and I get some pretty ugly looking waveforms in here. There's a long story about why that waveform looks the way it did, but somebody did want to pay the money when they built the building to put some filters in, right? Basically why it turned out that way. But that's not uncommon that you see that sort of thing happen in the real world. And Fourier series gives us a way to sort of think about and analyze those sorts of real world problems. Okay. All right, so to do this, I want to go back a little bit to the sine wave because there's basically 4 different ways that I can think of for thinking about a sine or a cosine. All right, the way we kind of always talk about, I'm going to call this here in this part of the class approach 1, which is to say any sine wave I see, any sine or cosine wave is identified by 3 parameters: an amplitude, a frequency, and a phase. Those are the 3 parameters that I think about. So I can think of that sine wave, though, in essentially 3 other ways. Okay. One of them is to say that at any given frequency, if I have something with some arbitrary phase shift, that I can use a trig identity and think of that somehow as the sum of a sine and a cosine at the same frequency. All right. That's one way to think of this thing. The other way to think of it is basically using this guy here. This was what I called Euler's identity, right? So we're going to get back to that. So Euler's identity basically says that I can think of this thing as 2. So we're just looking at that thing. It looks like a big pile of math. What does that approach number 3 to say that that waveform is equal to that thing? What is that? Somebody had to tell me in words, what does approach 3 mean? How am I representing that sinusoidal waveform in approach number 3 in words? You may not remember, or you may not have ever known, right? What is that?
Is that you're representing it with a real part and an imaginary part?
Yeah, I mean, so e to the j omega t, e to the negative j omega t. What are those 2 things? They're rotating vectors. They're 2 vectors that rotate in the complex plane. So this idea is I can have a cosine which sort of evolves over time. So if time is on the x-axis, then these things kind of evolve over time. But I can think of them in a complex plane as basically 2 real vectors, one rotating in the clockwise direction, one rotating in the counterclockwise direction. Or I can think of it as the real part of one rotating vector. All right. At first, it seems like, well, that seems weird to have 3 different ways of thinking about it. But it turns out, oftentimes, the exponential stuff makes the math a lot easier. Particularly makes the calculus a lot easier. All right. So going to phasors got rid of differential equations. That's nice. It makes our calculus easier, right? It's also going to make our calculus easier with this to use exponentials. All right. So we're going to try to focus on that at some point. All right, but we got to kind of gear ourselves up to try to understand and remember how these 4 different approaches all relate to each other, right? So if I have this, okay, so I said, okay, let's say I've got this waveform, C cosine omega t plus phi. For what I've shown right here, and I had a plan here. All right, I'm going to have to go out for a second. All right, so if I have this here, C cosine omega t plus phi, so C and phi. So C is the amplitude, right? So if I'm just looking at this, where on my y-axis is C defined? Yeah, so this is C. It's the peak value right here, right? What is phi for this particular waveform that I drew here in this picture? 0. Yeah, phi is 0. All right, so let's say I had something like this. 4 cosine omega t plus 45 degrees. All right, so we talked about shifting waveforms the other day. Plus 45 degrees. If I have a omega t plus something, which way do I go? Left or right?
Left.
Left, right? Left. Basically, that's an advance. When I have a plus, I'm basically advancing the waveform, meaning that the peak that occurs at t equal to 0 in the original cosine happened earlier in time. That's an advance of the waveform. So what I should do, that's why I went out of full screen here. Basically, this guy would get pulled something like that, right? So its peak would be somewhere farther ahead, right? So 4 cosine omega t plus 45 would look like this. So in other words, what I would see here is that when this guy crosses through the t equal to 0 line, right? That t equal to 0 line is moved somewhere down a little bit further. What would happen if I said that it was 4 cosine omega t plus 45 degrees, or sorry, plus 90 degrees? Let's make it 90 instead. How would I, and you should be able to tell me exactly where to put that. Right in the middle. Like that, right? Why right in the middle? If I shift it by 90 degrees, well, close. I've made it a minus sine wave, right? If I look at this picture right here, what I've turned this into is minus 4 sine omega t. How do I know it's minus? Because it's going down first. All right. So let's say I wanted to turn it into a 4. Let's cross that out. Let's say I wanted to turn it into 4 sine omega t without a minus sign. What would I need to do then? Yeah, so put it that way, right? So I delayed it by 90 degrees. So I hate remembering all those trig identities. And so you know, and they'll tell you in 2112, they'll say, what's the phasor for 4 sine omega t, right? And you got to realize that it's not 4. Half the class is going to put 4, and the other half of the class is going to put 4 angle negative 90, right? So what you have to do is, I mean, the way I think about that is I think about if I just took cosine, how do I have to shift it around left or right to be able to match what sine looks like? Okay. So anyway, this is a useful way of thinking about it. And of course, and the important thing is when I look at this, right, this would actually be minus 90 as I've drawn it right there, right? The important thing to think about this is whether I gave you sine or cosine or whatever, I can always think of it as some shifted version of cosine, right? That's the important thing. Any waveform can be thought of that way. I just need to figure out what the amplitude is and what the angle is. All right, so the other way of thinking about something like this, which turns out to be useful in some cases, is to say that if I give you some cosine waveform, right, that has some amplitude and some angle, I can think of that as a sum of sine and cosine. Now, if you wanted to figure out what A and B are in this particular case, right? So C and phi, the amplitude and the phase, relate to A and B. If I wanted to figure those out, what would I need to do? What would be the best way to figure those things out? In other words, let's say I wanted to derive A and B in terms of C and phi. If I wanted to derive those, where would I go? What do I need to do that? A trig identity, okay? If I told you, if you had this problem here, cosine alpha plus beta, you can go look that up online. Cosine alpha plus beta, anybody know what that would be? Probably not. All right. Somebody does know, all right? Cosine, like that. And then it becomes minus sine alpha sine beta. All right. If you look that up online, you'll find that. So if I look at this, what I did here is I said, well, let alpha equal omega t and let beta equal phi, right? And then I get this whole thing. So this is actually equal to C cosine phi cosine omega t minus C sine phi sine omega t. So this here is what I called A, and this here is what I call B, right? So A is equal to C times cosine of phi, C cosine phi, and B equals minus C sine phi. Okay. All right. Now you'll see in the book there's all sorts of formulas, right? I'm going to try to simplify it down to fewer of those because I find it tricky to have that, right? So let's look at an example then. What I've got here, and I should really go back to full screen. Hopefully it won't take forever like last time. All right, now it is. Okay. All right, not even going to stay in full screen very long here. Okay. All right, so say I got something like this: 2 cosine 2 pi 1000 t plus there we go. All right. Okay. Sorry. All right. So I got this. Okay. What I'm saying is this guy can be written as A cosine 2 pi 1000 t plus B sine 2 pi 1000 t. And if I take this waveform here and this waveform here and I sum them, then I get this guy. All right, so let's take a look at this here. So which one is which in this picture? All right, I can go back and I can figure out what, so A is equal to, so A was equal to here. So it says C times cosine of phi. Okay, what is A equal to here for this example? 2 times what? 2 times cosine of 45 degrees. So cosine of 45 degrees, if I calculated that, it would be square root of 2 over 2, right? So there'd be that. What's my B value? What was that one? Yeah, minus 2 sine 45 degrees. All right, so I drew the summation and this all on these axes right here. Which one's which? One of them's kind of light, but which one's which? So let's take a look at this yellow one here. Which one is the yellow one?
That would be B, right?
Yeah, this guy here is B sine omega t. What about the red one there? Yep, this guy is the A cosine omega t. And then the blue has to be the summation, right? So you can kind of see it sort of makes a little bit of sense, right? If I look at this point in particular, like this peak right here, right? That's the point at which both the yellow and the blue are crossing over each other. So the summation is going to be at its maximum value, right? But all three of those two things all look exactly the same, right? And if I look carefully right here, right, where this guy is crossing through, so 0 is right in the middle, where this guy is crossing through 0, it looks like this waveform, which we said was the B cosine omega t, and this one here, which is the A cosine omega t, are equal and opposite, right? So they add up to 0, right? So the summation here, if I added at each individual point in time, what I get is what I have right here. This 2 times cosine 2 pi 1000 t plus 45. Okay. All right, that's my overall summation. So that's another way of looking at one individual sine wave. Now we're going to use this when we have multiple sine waves. That's why we're trying to going through this. Is there's multiple ways of representing the Fourier series. All right. My third approach is this one here. Okay. We said this one was rotating vectors. So I said I shouldn't have stayed in that view, and I shouldn't have, because I'm now going to look at a Matlab example here. All right. So all right, this Matlab example, what I'm going to plot is not this one. I didn't want to do this one. Okay. Do that one next. Okay. All right. So here's this. I wanted to sort of try to visualize the relationships here. All right. So what I have is on the top, I've got the 2 rotating vectors plus their sum. All right, and I'm letting them rotate. And then what I see here in the middle is basically what they're tracing out. Okay. So in this particular case, the waveform I chose was 4 cosine omega t plus 45 degrees. All right, so if I look at this, what I can see is that I drew three things. So basically at the top, I've got the rotating vector. So if you watch those two vectors, they're rotating together. Now, it looks a little bit confusing because it looks like what they do, right? Looks like what they're doing is that they're going like this, and then basically they're flipping back and going the opposite direction. Is that what they're doing? Right, so watch it now. So now they're rotating. Okay, they're rotating. Now it looks like they're gonna just rotate directions, right? Is that what's happening? They're crossing over each other, right? So basically the one that was on top becomes on the bottom because they basically they're rotating in opposite directions of each other. So it looks like they're just flipping, right? But they're rotating in opposite directions of each other. What am I showing in the middle here? In the middle, it's the sum of those two things. So if you look at the useful thing about looking at that top picture is if I sum those two vectors, what's true about the imaginary parts of those vectors always? They cancel out. Their sum is always purely real. Okay. What have I shown at the bottom in that bottom picture? What are those two things? Those vectors don't rotate, do they? Yeah, they're static. So when I look at those two things, basically what are those? Well, in the context of this picture right here, this equation, right? Those two things are what? This, yeah, the part without the t. Yeah. So this guy here, I'm going to call this alpha 1, and I'm going to call this alpha minus 1. All right. And why I'm using 1, I'm going to talk about later. All right. But this is going to try to be consistent with the book. So I'm going to give those guys names alpha. And what they are, I mean, they're just complex numbers. They're what I call complex amplitudes. All right. For those phasors. Okay. So that's one way of thinking about this. And you can see if I told you I gave you c cosine omega t plus phi n, you should be pretty easily able to figure out for me alpha and alpha minus 1. Right? There's not a lot of hard work in that. All right. What about this other form? What will this look like if I draw this? So c cosine omega t plus phi n. So let's say I had 4 cosine omega t plus 45 degrees. What would that look like as time advances? This is a vector too, isn't it? Right? So in this case, that was the other one I did wrong first. Here we go. All right. So let's watch this one. All right. So basically what I see there is I have a vector rotating. What am I showing on the bottom of this image? What do you think the bottom is there? The top is that rotating vector. What do you think the bottom is? The bottom looks like a cosine, doesn't it? So when you see those X's kind of come in there, they trace out over time a cosine, don't they? So what do you think that is? How did I generate that? It's the real part of that vector that's rotating around. So every X I put in is the real part of that vector as it moves around. Now, what's this guy that's not moving? Well, that's the static phasor, right? That thing right there, that static phasor, stop this guy. The static phasor is this c e to the j phi. So in this case, that guy was 4 e to the j 45 degrees, or if I put it in polar, we just say 4 angle 45 degrees, right? So it's basically some vector that's sitting there not moving, right? So I have those 3 different ways of representing a sine wave, and I go through that again because it's going to be really useful to us as we get into this idea of Fourier series. On homework 6, I'm going to have you basically going back and forth between these different forms a little bit, all right? Because you guys got to get comfortable and used to that. Now, the reason for doing it basically is I can relate. We're going to talk about the Fourier series forms here in a little bit more detail, but basically there's a sine cosine version, what I call a shifted cosine version, and a complex version. And basically, if I have any one of them, I can easily move back and forth into the other kinds. what turns out is this is the simplest one for us to use for analysis. This one, when I say shifted cosine, this would be that C cosine omega t plus phi. This guy would be that C over 2 e to the j omega t plus C over 2 e to the minus j omega t. This is the easiest from a calculus perspective. All right, the one over here on the right. This one is ugly from a calculus perspective, but it's really intuitive from a circuit perspective, right? Because what circuits do is they change amplitudes and they change angles, okay? This guy is just really annoying over here. This guy would be cosine omega t plus sine omega t. Calculus-wise, he's awful, all right? There's no way about that, all right? But we can move back and forth. If I have the amplitudes and angle for one of them, I can easily move back and forth between them. All right, and I've got here sort of a summary of how you relate those two things for each other, which I'm not going to go over in detail, but you guys will probably look over those formulas. Like I said, there's probably, I don't know, it's like 80 formulas in that section 9. I'm not exaggerating. There's like 80 formulas in that section 9.1. It really, to me, kind of comes down to looking at this slide right here, and you can pretty easily make the relationships between the different types. Okay. All right. So what I want to do is with that basic stuff behind us. All right. Again, that stuff's really important to understand, and there'll be some questions about that on the homework. All right. The important thing is I want to understand, what do I do if I have this type of a waveform? All right. The whole idea of this idea of a Fourier series is that I can view this thing as the sum of sine waves that are all, what I said, harmonically related to each other. So let's kind of think about this for a second. So I have this picture here. All right, I'm just going to keep going with this thing. If I have this picture here. All right, so I have a square wave shown in blue. Okay. What have I done here by putting in that sine wave? So I put a sine wave at the same frequency as the square wave. It kind of looks like the square wave, doesn't it? All right. What I can do is I can begin to add additional waveforms to try to make this guy look like the square wave. Okay. So you can kind of see this. This guy, they have the same timing. These two waveforms, the square wave and the sine wave, have the same frequency. How can I make that look more like a sine wave? Or sorry, how can I make that sine wave look more like a square wave? What would I have to do to it to make it look more like a square wave? What's one thing, looking at this picture right here, what's one thing I have to do for sure? What's that? Scale it means somehow I need to make it bigger or smaller, and I'm gonna have to do some amount of scaling probably. But one thing that's maybe even more obvious, hopefully.
Increase the amplitude.
Well, if I increase the amplitude, so what I want to do is maybe I may be more clear. I want to get the sine wave kind of fitting right into that square wave. So increasing the amplitude maybe, but if I wanted to kind of fit it in there, the first thing I would do is I would shift it up. Right? So in other words, I would add a constant to it. All right, so the difference between this picture here on slide 21 and this picture on slide 22 is what? What have I done to the sine wave between those two slides? I added 1. Okay, I added a constant 1. So in other words, what I have right here in this slide, this guy right here is what I'm going to call B1 sine omega t. And I'm going to say for this, I have 1 plus B1 sine omega t. Now the amplitude is kind of weird. If I went through and I really looked at the amplitude of that thing, what I would find is the amplitude, there's no reason for you to know this, is 4 over pi. Okay. No reason for you to know that just yet. Let's say I want to keep adding stuff. So I want to keep adding sine waves to that existing sine wave to get it closer to the square wave, right? So what I can do is I could do this, all right? What have I done here? So in this particular case, what I actually am looking at here, this guy is 1 plus B1 sine omega t, where omega is the same frequency as that square wave. And I've added to this guy what I call a third harmonic. All right, so this is what I call a third harmonic. In other words, what this is it's a waveform that has 3 times the frequency of the original. Okay, so it's a third harmonic, and I keep going with that. All right, so here, here what I've got is a fifth harmonic. 1 plus. What's going on? All right, 1 plus B1 sine omega t plus B3 sine 3 omega t plus, in this case, I've added what I call a fifth harmonic, sine 5 omega t. All right, so I got a whole bunch of stuff now. Here, this last picture, what I've done is I've actually added in 99 harmonic. Okay, now you can see if I look at these things, it's getting pretty close. That summation now is to that square wave. Now, if you look at this, right, each of these guys has different amplitudes. What do you think is true, just intuitively, right? The amplitude of this guy said was 4 over pi. All right, the sine wave here. When I added the third harmonic, do you think that that third harmonic, that sine 3 omega t, do you think its amplitude was bigger or smaller than the amplitude of this one? Smaller. All right, so it's definitely yeah.
So what about the second harmonic?
That's a good question. I didn't include those, because if I included those, they wouldn't actually fit in there. And that's a great question, right? So if I included the second harmonic, what would the second harmonic look like? The second harmonic would have twice the frequency. So what would that look like? Well, that means that in half the period, he would go through 1 period like that. This guy here, this is sine B1 sine omega t. This would be B2 sine 2 omega t. If I looked at this, and again, I'm just being intuitive, there's a way to figure out the amplitude of B1 and the amplitude of B2. We're going to figure out the math to do that, right? But just intuitively, if I look at this, if I take this waveform here with twice the frequency, what I'm going to see is this doesn't really fit, because I'm adding some and then subtracting some. If I added this to that sine wave, it wouldn't fit in there. All right, so that's not necessarily intuitively obvious. I might have to do some math to show that. What it turns out, if I do the math, I basically find that if I add what I call odd harmonics, so the first, the third, the fifth, et cetera, that what I end up getting is something that looks almost exactly the same. Now, they got these little dog ears here that kind of form. All right, that happens because in reality, it takes an infinite number of those sine waves to exactly equal that square wave. If I had an infinite number of them, the dog ears would disappear. But if I only did, in this case, I did up to n equal 99. Right? With n equal to 99, I get some of these dog ears. But the basic idea here is that I can take these sine waves and add them up. And if I looked at this, the math is such that at the nth harmonic, the amplitudes are 4 over n pi. So as n gets to be bigger, that amplitude gets smaller and smaller and smaller and smaller. And I keep adding in smaller and smaller sine waves. Now, again, we got to figure out the math to do this. But what this says is if I have a square wave like this, that square wave can be thought of as essentially a sum of a bunch of sine waves, which means that I can view a voltage source as a superposition of a bunch of sine waves. All right, that turns out to be a really useful way for me to think. So our definition of the Fourier series, there's ultimately 3 representations that we use for the Fourier series. All right, this is the first one that we're going to use. All right, it's the sum of sine and cosines like this. Now I want to unpack this statement because I think this is a tricky statement for people when they look at this. For a lot of students, I think you see that for the first time and that looks like a strange thing. All right, when I see this summation here, help me out. So f of t is equal to a0 of t. All right, we're talking about what that is. But how would I interpret this summation here? N equal 1 to infinity. Help me out. How would I expand that sum?
Is that designed to cover all your harmonics?
Covers all my harmonics, yeah. So how would I go through this? How would I expand that summation? So with n equals 1, right? I would say what? Yeah, a1 cosine omega naught t plus b1 sine omega naught t. Okay. Plus what? What's the next thing I would add to this? Yep, a2 cosine omega naught, or 2 omega naught t. Yeah, 2 omega naught t plus b2 sine 2 omega naught t. Plus what? Keep going. Yeah, plus a3 cosine 3 omega naught t plus b3 sine 3 omega naught t. So this guy just keeps going like this. And I'll write it down here, right? So it goes on forever, technically. And these guys, I'm going to give a name to here, and then these and these. I'm going to say this is my first harmonic term, or what I call sometimes the fundamental term. Because the frequency of that thing sets the frequency of everything else. So we call it the fundamental. Okay. This here is what I call my second harmonic. This here is what I call my third harmonic. All right. Now there's a formula for the amplitudes A1, A2, B2, all that sort of stuff. If you want to find how to derive those amplitudes, I'm not going to derive them here. All right. You can find the derivation in the book, and some of you guys will want to see that. Right. It's not hard to do it. I'm not going to work through it here. I think it's easier for you to just understand what a Fourier series really is. To me, that's a lot more important than deriving it. All right. So some core definitions that we need to have. All right. One is the fundamental period or frequency is the smallest period of the waveform. The smallest period of the waveform. Right. That is what I define to be my fundamental frequency. So we're gonna find some ways to do that. And then I have this thing here called the harmonic number. All right, the harmonic number n. So if I have a fundamental frequency f naught, then my harmonic frequencies are n f naught. Okay. All right. So here's how I think of that. I like to think of it this way. When I look at this picture right here, I like, as an engineer, I think in terms of pictures better than I think in terms of just straight math. I look at this here, what I see, that equation at the bottom, I think of it like this. There are essentially a set of what I call basis functions, right? Sine and cosine. Sine 2 omega and cosine 2 omega. Sine 3 omega and cosine 3 omega. These are sort of basic waveforms. What I'm saying is I take that waveform and I multiply it by some amplitude, and then I add it to all the other ones to create my square wave. Okay? That's what Fourier series is doing. It's all about determining the values of A1, B1, A2, B2, so on and so forth. Okay. Now, what about this guy up here? I have this A naught over 2. That guy is multiplying a constant. Okay. If I have a frequency of a term that is constant, that has 0 frequency, right? The frequency of a constant is 0. In other words, it doesn't vary. Its period is infinite. Okay. What do I call this? The term I'm going to use is that this is a DC waveform, right? Something that has 0 frequency is DC. All right. So if I looked at this and we went through this here, I said that my amplitudes my B sub n's were equal to 4 over pi, or 4 over pi times n, I guess was what I said. If I looked at this, that means that this guy has no cosine. So all of my A values are 0. And my B value, this guy was 4 over pi. This one here is 0 because I said it didn't have second harmonic. This one is 4 over 3 pi because I do have third harmonic. And so basically the goal in Fourier analysis typically is I'm going to present you with a waveform like this square wave. And what you're going to do is you're going to say, all right, I want to figure out what is the value of A1 and B1 and A2 and B2. That's our goal, is to figure out those amplitudes. In other words, what amplitudes of those individual basis sine waves do I need to create that square wave? All right, that's going to be the primary function that you have. Okay. All right, so what I want to do is I want to look at an example here. All right, so let's say I've got this guy. That is a periodic waveform. It's an ugly periodic waveform, but it's a periodic waveform. Okay. I didn't bring my notes with me, so I'm going to have to think about this one on the fly. Looking at this guy right here. Looking at this guy right here. All right, so I have multiple steps that I need to take. This guy is a periodic waveform. How can I tell that it's periodic? It's ugly looking. Look at that picture. And how can I tell that's periodic?
It repeats.
It repeats, right? So as I go from here to here, that guy repeats. So if I wanted to figure out the period of this thing, how would I figure out the period? What are the ways that I actually have two ways to find a period, right? How would I find a period? Well, what's omega here? I can't, looking at this, I can't really tell what omega is. Can you? Well, one way to do this, so what I did, I plotted it in Matlab and I said, all right, what's the time between two peaks? Right, so I know that it repeats over this time period. And so I did a data tip here and I said one of these is if I zoom in on that, right, 0.005 and 0.0001, right? So this guy works out to be a period of 4 milliseconds, or a frequency. What would the frequency be? The period's 4 milliseconds. What's the frequency?
0.25 hertz.
1 over 0.004, which works out to be 250.
Okay.
Yeah, you got the right idea. All right. So 4 milliseconds leads to 250 hertz. So the other way of looking at something like this is if I have something like I've given you here. All right. So notice these guys clearly, these are weird. 1000, 1750, 1500. I said so the smallest period, all right, the largest period is the fundamental frequency. The largest period corresponds to the fundamental frequency. All right. So one way to determine that, the book talks about this, is to look for something called the GCD, or the greatest common divisor. Something you probably haven't thought about since middle school or something. All right, the greatest common divisor. All right, so in this case, what I did was I said, all right, well, I look at this. This guy's got 1000, 1750, and 1500. The greatest common divisor of those things, MATLAB has a tool called GCD, and it tells me the greatest common divisor is 250. So this guy has a fundamental frequency of 250 hertz. So the first set of problems that I'm going to give you in the homework is basically going to be to look at something like this and to figure out for me. So step one will be to figure out what is the fundamental frequency. And then to figure out, step two here is to figure out the A sub n and B sub n values. All right, so that's going to be your next step, is to figure those out. Okay. Now, so when I look at this here, all right, let's keep going with this particular example, right? So I figured out that F naught, the fundamental frequency, was 250 hertz. So what I want to do is make a little table for myself and figure out which harmonics are here. I guess in terms of the way I define this, this is really my step 3. All right. My step 2, which should be up here, is to figure out which harmonics are there. All right, which harmonics am I actually using? So looking at this picture right here, which harmonics do I have? Well, so my fundamental is for what? So the fundamental frequency is for which value of n? 1. All right, so looking at this guy, do I have a fundamental in it? No. All right, he actually doesn't have a fundamental sine wave in it. All right, so there's no fundamental sine wave here. So I'm going to say this guy is 250. Now he also has something for n equal to 0, right? For n equal to 0, what frequency do I have? 0 times 250 is what? 0. So this guy has a 0 term, a DC term in it, okay? So let's see, I got a second, a third, a fourth, a fifth, a sixth, a seventh. All right, let's keep going with this. All right, what frequency is my second harmonic here? 500. All right, so let's do a check. Do I have a DC term here? Do I have a 0 frequency term? Yes. Okay. Do I have a fundamental? No. Do I have a 500 hertz? No. Let's see, what's next? What's the third harmonic? 750. Do I have any of that? No. All right, do I have a fourth harmonic? What's the fourth? 1,000, right? So I got 1,000. Do I have that? Yeah, I do, right? How about fifth harmonic? What would that be? That would be 1250, wouldn't it? Right, do I have that? No.
I'm sorry, I'm just like confused. Like, well, where did you find out this is 1250? It's not. There's no harmonic.
Well, so what I'm doing is I'm looking at this waveform right here, and I'm seeing I don't have that. So I gave you the equation for this, right? Maybe that's the part you're missing, right? So I have a 2 pi 1000, I have a 2 pi 1750, and a 2 pi 1500, right? So the sixth harmonic would be 1500. Do I have that? Yes. All right. My seventh harmonic is 1750. Do I have that? Yes. All right. Now the question would be, what are the amplitudes at those frequencies? All right. So did I copy over? I didn't. So the form of the equation we said was A naught over 2 plus summation A n cosine n omega naught t plus B n sine n omega naught t, like that. Okay. So let's talk here. What's our A n values and our B n values? We're gonna do more examples. We're gonna do a lot of examples next week. But look at this, A n and B n values. All right. So I don't have anything for these guys because those harmonics don't exist, right? What about there at the fourth harmonic? What's the A n value and what's the B n value? So looking at that expression right there, fourth harmonic was this guy, 1000. What's my A and B values there? 50 and 0, right? Because I have a cosine term but no sine term, right? So I would say I have 50 and 0. I don't know why I got that big line like that, right? And then it would be similar, right? So 1250, right? Do I have anything for that? No. Then what do I have? I have a sine term at 1500. So what's my A value? 0, and my B value is 2. At 1750, it's 0 and 20. Right, so I figured out by inspection there what my values are. Okay, so I can do that by inspection. Now there is a calculus way to figure it out as well. If I have something that's not a sum of sine waves, like obvious like this, like the way I've given this is, you know, it's this sine plus this sine plus this sine. Well, if I gave you a square wave, right? If my picture was a square wave and I said to you, well, figure out the amplitudes. Well, that takes a calculation process to do. I can't do it by inspection. That's what we got to start talking about on Monday. All right. So we'll start there. I think the next class has an exam today, so I'm going to stop myself.